Alright, silly people, here's the situation. We are given a equation of motion for the classical harmonic oscillator, which is this guy, um, and given the objective of calculating a bunch of randomly distributed um, positions for the harmonic oscillator um, for a bunch of random times and checking that our probability distribution that we got in like the first part of this problem, I think question 11, is good. And so that is the general like effective probability distribution that we were using for that problem. And so I'm going to put this in a form that is a little bit nicer. So before I made the um, substitution of period is equal to 2 pi over omega, so I'm just going to do that here. And also factor out an m over k, right? And then we have in here, we have 1 over 2e over k minus kx squared. And of course, the frequency of the simple harmonic oscillator is just k over m. So this term actually cancels out this term. The 2's cancel out, so you have 1 over pi. And then we also found that the amplitude of the motion was just a is equal to 2e over k under a square root. So actually, in the radical, we can rewrite this as being 1 over a squared minus kx squared. And actually not even k anymore, just x squared. Made an error there. Yeah. So it's 1 over pi square root of 1 over a squared minus x squared. So that's the probability distribution that we're going to be turning into code. And for the problem, it says that you can set a and omega both equal to 1. So that's also what we're going to do. Alright, so instead of doing Mathematica like Griffiths suggests, I'm going to do it in Python because it's my native computing language. So let's set this up. So we're going to do, well, first let me import the relevant packages actually. That would be matplotlib, pylab, as plt. Let me do numpy. And then we can set up the parameters that we need. Those being the amplitude, which we're going to be set to 1, and omega is also going to be set to 1. So I'm just going to make omega look like W and set it equal to 1. And we need to do 1,000 or 10,000 positions, so 1,000 there. Alright, now we need to get our probability distribution in here. So let's define rho of x and a as being returning 1 over, we'll do np dot pi times np dot square root of a squared, so a squared minus x squared. Cool. Now we need to generate 10,000 random times and the corresponding positions. So we're going to get our time from the random package, so numpy.random. We're going to do the uniform distribution between, we're going to run it between 0 and 100 seconds. I think that'll be fair enough. And then for 10,000 times. So that's that. And then the position for each of those is the function that Griffiths gave us as being a times the cosine of omega t, so w star t. Okay. Then the probability distribution. So let's create a domain for ourselves using the linspace function from NumPy. Let's run from -a plus 0.1 because we don't want to divide over 0. Trust. And then that's going to be going to a minus 0.1. And we're going to do that. I'm going to say also do that 10,000 times because why not? And then we can generate a list to output our probability distribution as just being running it through our function of x and a. And then we want to plot these guys now. Best way to plot these is on the same subplot. So we're going to create a subplot using the subplots function within matplotlib. And we're going to stack them like that, so one graph on top of the other. Let's just generate the first graph. It'll be a line plot, and it'll be our probability distribution. Let's make it blue. Actually, let's make it green. And then let's do a histogram of our random positions. So that's going to be histogram of x with 50 bins roughly. And that should be fine. And yeah, so let's make those plots. There they are. So you can see on the top, there's the probability distribution. It's not normalized, but it is, I think it is normalized actually, and it's just going like that. And then here are all of our randomly generated points on this interval. And it looks like it pretty much matches the probability distribution that we gave. If we allow for more bins, maybe it will look a little bit smoother. We can rerun it. Yeesh. That's not too much more insightful, but you know, maybe just 100 is best. Well, okay. Anyway, the probability distribution is good, and this numerical method proved it. All right.